Hello, hello. All right, check this out. Back after a few weeks for me, hiatus anyway. And the last place, I think, the last lecture in the course, it's labeled Lecture 8 on YouTube. Man, I really should have reviewed this just a few minutes ago before I decided to record this. But anyway, following up on that material about mass extinctions, I wanted to transition this part of the course off of that topic into sort of modern times, or into the Cenozoic, the last 65 million years, or since the last mass extinction. And more exclusively, as it's now kind of crunch time in the course, to really focus on the last or the current catastrophic event that's occurring globally and worldwide, that in some cases is just as catastrophic as the asteroid impact or other major catastrophes that we talked about in the course. After this material, I'll kind of add a few videos of random material that was fit into the course at different times, at least this term, which is, what is this, winter term 2019. It's actually spring break. We're basically done, or we're done with the former term, which would include mega floods, super volcanoes, and other things. Now, on to back to today's topic. Whatever. This material comes on the tails of the discussion of mass extinctions, and then more than talking about the extinction itself and the causes, I want to look at what happens biologically, or at least what we can tell on the fossil record, what occurs to the organisms that make it through those mass extinctions, which is something we've toyed with before. We've discussed a little bit during the Great Oxygenation event, and oxygen becoming a really relevant part of the biosphere, or at least what the biosphere had to contend with. And then also with the rise of dinosaurs after the Permo-Triassic mass extinction. So this has been salted in there a little bit, but now I want to exclusively focus on that. So we'll discuss a little bit mass extinctions and climactic forces that cause change, biologic change in organisms. And then, of course, we'll come to the group that we belong to, the hominids, because, like egotistically, this is all about us, right? We're the major players here. It's humans that are watching the video here. I, made the lecture and got the power going on, and I'm human. So I think sometimes, though we are not, that was all a joke, by the way, right? And being facetious. Even though this is a natural history course, right? The Earth history. We sometimes do, even in natural history, we come down to let's study the human system, because that's clearly very important. And it's not solely because we're egotistical and we want to know just about ourselves, but actually, in context of this class, Violent Earth, the presence of our species on this planet over, not even since the origins of our species, well over 300,000 years ago, as we'll discuss, is becoming, or has become, a major catastrophic force on Earth, which will transition to that discussion. Mostly during the following lecture, we'll focus on this quite a bit more. Humans, or Homo sapiens, as a geologic force. We are a raw geologic force, that of which the Earth has never seen. Now, to recap a little bit, this is actually probably more relevant for me than anybody who's been watching the lectures at a regular pace. But we started with cosmic web, very large scale, and how sort of fractally that large scale matches the smaller scale of, or the more minute details of the universe, things like our neural networks or the mycelial networks in a forest. We did discuss the origins of solar systems, really our solar system and the accretionary disk, briefly. The ignition of the sun, the first main catastrophe that we discussed, which was the impact of the planetesimal Theia with the Earth, the big impact hypothesis, and then the iron catastrophe, which is a discussion on the layering of the Earth. We took kind of little side there early in the term to focus on some Earth processes. What is the Earth made of? What do rocks look like? What's evidence for the the structure of the interior of the Earth? That type of stuff. Introduction to plate tectonics. Discussed about a little bit about the driving forces of plate tectonics, slab pull as opposed to a little bit of ridge push, and just how important these boundaries are for not only for the face of the Earth or the surface of the Earth, the face that you may see from outer space, but also the dynamic inner workings of the Earth that have kind of kept this planet habitable since the inception of life. And I know I've said this and stressed this a number of times of the very unique crustal, thick crustal silicate blanket or insulating blanket that is helping the Earth retain its internal primordial heat, and it just keeps ticking. And that whole system, all of the systems are integrated and working sort of in tandem together as a system of checks and balances and responses to sort of have this almost homeostatic-like balance that has been called Gaia, of course, in the past, or Earth system sciences today. Then we, of course, talked a bit about volcanism. And though we haven't talked about the really violent volcanism quite yet, that'll come in one of the sort of side random lectures after this last topic. But we did talk about some of the large eruptions that have occurred in kind of in human history and in sort of human prehistory. So the example here is about 7,000 years ago, the eruption of Mount Mazama, which is outside of what we might normally consider human written history. Of course, maybe there's languages like cuneiform and Samaria that are being developed at that time. But the indigenous folks here in the Pacific Northwest had no written record, and so sometimes that's tossed aside as being prehistory or human prehistory. And it certainly is part of history, humanly, and it's also embedded in the rocks as geologic history. So here we are, Mount Mazama, gigantic, huge eruption, many times larger than Mount St. Helens, and it's still just a drop in the bucket of what this planet does as far as violent volcanism. Okay, then actually just over the weekend, and I'll put this in as a side comment, remember Mount St. Helens is 1 cubic kilometer of ash. Last weekend, I led a geology field trip, a geology tour for the Friends of the Oahe local conservation group that works in the Oahe Mountains and Oahe watershed. And we went to Sucker Creek State Natural Area here in Oregon in the Oahe. And the formations that are exposed there, one of the main formations that's exposed around the corner is called the Tuff of Leslie Gulch, or the Leslie Gulch Tuff. Beautiful, beautiful gulch, beautiful rock in general, very, very beautiful weathering pattern. Maybe I'll put a link in the show notes or something like that to some of the beautiful scenery that's there. Anyway, my point is that formation, the Leslie Gulch Tuff, by volume was about 650 cubic kilometers of ash just outside of where I live here, just outside of where I am, this huge supervolcano-style eruption. And it still just blows my mind to be on a landscape of volcanic tuff or volcanic rocks, and to think about the immensity of that event when I look at pictures of Mount St. Helens, the huge ash cloud or the landslide and pyroclastic eruptions or pyroclastic flows, and just the immensity of that event is incredibly scary and violent in this natural way, right? So it still surprises me to be looking at rocks that are representative of huge eruptions like this. Okay, Wilson cycle and tectonics. We had taken some early divergence in a place that's quite a bit later in the time loop of Snowball Earth, another major early catastrophic event about 700 million years ago that really the Earth was largely glaciated, and that's quite different from the more recent Pleistocene glaciation that we have record of all over the Earth. It was just a mere 2.5 million years ago to 10,000, or about 11,500 years ago to last glacial maximum. during which time many of these megafaunal, mega for large, mega scale, and fauna for animals, megafaunal beasts existed during that time, right? The large, the glyptodons and your giant tree sloths and things like this, or giant sloths. Then we did then begin discussing mass extinctions, not necessarily head-on at first, but we first discussed the Chicxulub impact crater and the evidence for that as a way to talk about asteroid impacts, which we looked at a few others, and we talked about the near-Earth asteroids and the possibilities and knowledge that we have of potentially upcoming impacts in our next thousands of years, and how important it is that we take a look at those things and have an idea about those, because we know what can happen to the planet when these things, of course, impact us. Then we also talked about the rise of atmospheric oxygen at some point and how catastrophic that event was, even though that's something that is very, very inherent to us to have oxygen in the atmosphere. It's essential to us as oxygen-respiring organisms that we have that precious, precious molecule that wasn't even present over 2.5 billion years ago, or maybe 2.8 billion years ago, at the beginning of the rise of oxygen that was first recorded, remember, as the banded iron formations in the ocean, which today is one of the greatest iron resources that we have on Earth. And a whole lot of the iron that you and I use as human citizens of this Earth, a lot of that iron is from the deposits of this time frame. Okay. Then from there, we began to discuss mass extinction a little bit more head-on. And one of the, I don't want to say like the poster child there, but one of the ones that we focused quite a bit on at that time was the Devonian mass extinction, and which, recall, was actually under the underlying causes were related to life emerging from the oceans and colonizing the surface of the land, because those plants, those newfound plants, were releasing organic acids that led to increased erosion, and that erosion led to nutrifying the oceans, large algal blooms, and some eutrophication of the ocean and cutting off the oxygen loop to deeper organisms. So that led to a catastrophic trophic failure of organisms that then, led to a very large mass extinction, the Devonian extinction. So that's basically where we end up today. Wow, that actually kind of felt good to me to review a little bit of this. It's been quite a while since I stepped back into Violent Earth mode. I've been doing a lot of other things, and I love this class, and it's so nice to see what kind of topics we've already been over and recorded. All right, now first of all, this is whether you're watching this kind of casually or are really in one of these classes and trying to do this material as work, and remember, you can find the assignments and lecture slides and notes and exams even and things like that on my website. I should link to that again if I haven't already. But whatever context or whatever you're using these videos for, hopefully for learning in any of those places you're at, I would like you to think about this. Of course, you don't need to get in groups of 2 or 3, right? That's only for when we're doing this as an in-class exercise. But what I would like people to do is to really reflect on those 5 major mass extinctions. And if you make a short list of those, 1, 2, 3, 4, and 5, and you think of course, when those were, and from collecting this from memory, we'll look at these in just a second. And then with that list and of the ages or the names of those, right, say like Devonian mass extinction, or Cretaceous mass extinction, 65 million years ago. Begin to list the causes of those extinctions in a couple of words, right, and maybe some details. So say, for instance, 65 million years ago, the Cretaceous tertiary mass extinction or Cretaceous Paleogene mass extinction caused by asteroid that impacted the Earth. Okay, so that's kind of the first part of this, is just to recollect those facts in your mind, or what we know of those extinctions. And then I want you to kind of think about the three underlying causes, or I want you to take those 5 and to put them into 3 separate bins, if you will. And I think there's you can choose the bin or the group here on your own, but I think there's really 3 natural groups that begin to be broken up out of that. So, the next slide here is going to give that material away. So, if you're interested in challenging yourself and doing this, you should go ahead and do that, because it is relatively enlightening to find that these 3 bins here essentially separate out into asteroid impacts. Of course, that's it's not like it goes without saying, but that's clearly one that is very devastating to the Earth. And then another one that really has only happened once is volcanism. And if you recall, that the Siberian traps weren't the only cause of the Permo-Triassic mass extinction. That was also it erupted through coal, right? All of those lavas were erupting up through lithosphere, or crust of the Earth, that was heavy, or not heavy, but it was laden with coal deposits of the Carboniferous. So that was kind of extenuating circumstances. There's certainly argument whether volcanism alone could cause a mass extinction. And the case that we have 250 million years ago, it wasn't just volcanism. You can put that as one of these bins. It is a natural bin that comes out of that, asteroids, volcanism. But that volcanism was special because of the coal. And then the third one? Yeah, life, right? Life. The Devonian mass extinction was essentially caused by life. Yes, it was eutrophication of the ocean, or it was organic acids that caused increased erosion. But life was the underlying cause there, right? Or then you have, and this is not included in these 5, but the rise of atmospheric oxygen and all the creatures, the unknown hundreds of types of bacteria that existed at that time that were maybe non-photosynthetic, methanogens, sulfur reducers, chemosynthesize, all these kind of things, and many of those met their end, or met their extinction, and were replaced by the photosynthesizers, because all of those other things were poisoned by the oxygen output of the other organisms. So that can be considered even a first mass extinction, the global first mass extinction, but we don't usually include it in geology because we don't have that level of record of the species that existed before and after. So really the only one caused by life here is the late Devonian mass extinction. Okay, there's 2 of them that are thought to be caused by asteroid impacts, and that is the Cretaceous Paleogene impact, the Triassic-Jurassic impact, and then the Permo-Triassic is, of course, volcanism. I left out, and maybe you did the same, or maybe not. I asked you to put them into bins, so you probably put it into some bin, the Ordovician-Silurian mass extinction, which there's a lot less that's known about it. I mean, there's plenty of scientists that are working on the paleontologists to look at this material. I don't mean to always brush something off as we know little about it because it's geology or something like this. But really, there are barriers to understanding the full extent of the causes and repercussions in this mass extinction, because these were all marine organisms at this time. And so there's knowledge and an understanding that a major decrease in the population occurred, but we have less of a record of the impacts of those individual creatures. But it was very likely to be some sort of climactic change that caused the Ordovician-Silurian mass extinction. And that climactic change may have been driven by, it probably was not driven by life of the marine oceans. There's no evidence that it was driven by an impact crater, and to my knowledge, there isn't discussion of it being volcanically related. So we're left with climate change and how. Okay, now we'll come kind of back to this, but I want to say one thing about, while we're on the idea of climate change causing mass extinctions, is that a changing climate causes changes, period. Okay, and now one of the responses in this ecological community was, unfortunately, a collapse of that ecological community, because the changes could not be adapted to enough, quickly enough. Excuse me. So many creatures went extinct. Okay, climatic change, of course, the plants and other things like fungi that are producing organic acids. Didn't I say that all like nonchalantly? Like, oh yeah, just like fungi. Man, you like get really excited about saying that word, right? So plants and fungi that are releasing organic acids during the Devonian are likely the responsible party for creating the two-step process to the Devonian extinction. Then during the Permo-Triassic, the Siberian Traps, a large igneous province of volcanism, erupted up through coal and led to a rapid increase in carbon dioxide, which caused actually not just global climatic change, which is usually what you would think is kind of inferred when I said this, or you may think that because CO2, carbon dioxide in the atmosphere today, we usually associate that with climate change, and not that it wasn't at this time, but also so much carbon dioxide in the atmosphere also caused respiratory problems, or getting enough oxygen, right? This also caused carbon dioxide poisoning of species and of animals. So this wasn't just a climactic change, that was also associated with this. But this literally had an effect on organisms one by one and personally that led to their demise, which is not that dissimilar from something like the Cretaceous Paleogene mass extinction, that the organisms were impacted by the impactor as well, or they were blasted by it. So there were populations of species that were directly affected by the CO2 poisoning, by an impact, where that's quite a bit different from this more passive style of mass extinction, where the organic acids that were producing or that were leading to increased erosion and then eutrophication in the oceans, that was a slower, less punctuated process than an asteroid impact, if you see what I'm going for there. The Triassic-Jurassic mass extinction, at least to my knowledge and some of the not-so-recent reading up that I had done, and then, of course, in the Ritalik 99 article that was cited in the mass extinction lecture, it's thought to be maybe a double asteroid impact. And now this is one that I could probably do myself a favor and to explore a little bit more deeply. It's been a while since I've looked at the Triassic-Jurassic mass extinction. So that would go in the bin of asteroids. That would go in the bin of asteroid impacts. And then, of course, we have, which is not really the primary topic today, is the potential of a sixth mass extinction. And I want to restate that. The potential for a sixth mass extinction. This is highly debated in the scientific community, and this is something we'll go over in the next few lectures. If and as this is occurring, this has many factors and many facets to it that are related all in some way to what we might call overconsumption of one species. So say you have in some cases I hate this analogy, but it does very good here, of a bacteria in a petri dish that reaches the end of its food supply and then it reaches its end, right? It consumed all of what it had available and overconsumed that and then read its demise. And that's just the fate of any organism that has a finite amount of resources or food available to it, which may be very well the case for us overall, globally, with all animals. And then to... a reference for this, there was a really good book, I want to say this was out in 2004, maybe 2005, The Sixth Mass Extinction, Elizabeth Colbert, and this is a really good kind of soft science book that goes through a lot of the setting up the ideas for this mass extinction. And another term that can be used here is called the Holocene extinction, or over the last 10,000 years, the demise of the large megafaunal beasts of the Pleistocene. We have seen those go extinct, and some of those have been demonstrated to be the fault of overhunting from humans, but others have actually been demonstrated to have nothing to do with humans and just climate change being the main factor. Now, whether or not it's human-induced, those species have gone extinct, and species are readily going extinct. In this pie graph, it's not really a graph, but it also discusses that many species are threatened and endangered, and many more are potentially threatened and endangered, or if already not extinct. Okay? All right, so that's kind of to get back to mass extinctions, just so that's really on the back of your mind palette right now as we move on. What happened, and this is a slide from that earlier lecture. Now, what happened during the Triassic-Jurassic mass extinction, not necessarily the processes up here, but I want to look at the taxonomic results, right? Here's during the Triassic and Jurassic, separated in time right here. The species of reptiles and amphibia that show up over here are relatively few that actually make it out here to the Jurassic. Where those that are conveniently highlighted in yellow here, the dinosaurs, all of those make it through to the Jurassic from the Triassic. So the fundamental not cause of the extinction, but the fundamental biologic result of the extinction was essentially to make room for new species. I mean, that's maybe not the purpose, but that was the result, is room was made for new creatures to find new niches to evolve into. And so the case was made in that last lecture about mass extinctions, that sometimes mass extinctions create opportunities for others, like we saw with fungi. I really hope that I showed that slide. Fungi after the Cretaceous-Paleogene mass extinction, and just a couple million years afterwards, all we see in the rock record as far as fossils are the fossils of spores that were being just thrown off from the giant fungal blooms that were occurring at that time. So opportunity was made for the decomposers of Earth after the mass extinction, and then it was organisms that allied with those, or at least harvested, and were able to make to use those things, or the results of those, that were able to make it through further after the mass extinction. Okay, now another example that I want to show of the impact on morphology or paleontology, just organisms, biologic morphology, is the ammonoids. These are a really, really cool fossil. I really hope that you've seen pictures of these things before, or, you know, I actually find it more and more common today that this type of symbology, the spiral symbology, and even ammonoids themselves. I've seen a few people, non-paleontologists, with tattoos of ammonoids, which I think is pretty interesting. So there's some sort of cultural awareness about the what might be referred to sometimes as the sacred geometry around the spiral or the Fibonacci sequence, and all those kind of things. So I hope that you've come across this fossil in the past. And now these are different than today's modern day nautilus. And those are a species that exist today. They are in the oceans, and they've been around since the Cambrian time period. They are a cousin of the ammonoid, or they are a different genus, certainly, maybe even a different family of organisms. But what this organism, it's essentially a squid. They're in the cephalopod order, and so like squids, and those things, this is the shell. It has, of course, most of its head in the shell, some eyes that are sticking out here, and then these tentacles that are out here, and those tentacles are used to get its food and to crush and consume its food in through its shell, and then probably out through some other similar siphon hole on the outside of the shell. Now, what this shell is for, in the case of the nautiloid and the ammonoid, are chambers to either hold water or to hold gas. And so why would this organism want to hold gas? Well, remember, gas is buoyant in the liquid. So if you have your half your shell that's filled with gas, you have more buoyancy to lift you up in the water than if you only had a little bit of your shell filled with gas, right? So then under that case, more water would make you sink lower. And that's exactly what these creatures do, is they repel, or they jet out gases for propulsion. So they're using it both for propulsion as well as for buoyancy to get higher and lower in the water column. Now, crudely, the nautiloid that's shown here, or crudely, the very early ammonoids that are here, it's shown that these are boundaries between the septa, just like your nose has a septa, a boundary between those two things. There's a boundary between each one of these cavities here, the septa, and you can see very early on, these were relatively simple shaped septa. And that didn't give the creatures a whole lot of control on how much gas they were releasing and taking back in for buoyancy. And slowly over time, as these creatures became more, they're carnivorous, and they're actually really good hunters of shellfish. And as they became, I think, more predatorial and more acute at being able to do that, pretty high sensor or high predators, the shells became more highly dissected so they could fine-tune the amounts of gases that are being released and fine-tune the amounts of buoyancy of where they were going in the water column to be able to chase prey, as far as I understand. So these are really amazing creatures. So that's the morphology, how it changed through time. But I also want to, so this, you can actually tell the difference in the time period of the ammonites by looking at their shell. If you found one in the field and you saw that its shell was all crazy and dissected into these crazy looking flowers, that might be as young as a Jurassic or a Cretaceous age ammonoid. Where if you saw one like this that was quite a bit more simple, you see the spiral shell, but the septa are all, very, they're not as delicately interwoven. That one you might read as maybe a Devonian age ammonite or something like this. Now, morphology changed through time. You can see that there's some punctuated changes after the extinctions as well, but these things went completely extinct 65 million years ago with the dinosaurs. These creatures actually suffered the mass extinction and are no longer around. Poor little ammonoids. Okay, so the Cretaceous, and now I'll just say one or two words about the dinosaurs changing morphology as well. The age of the dinosaurs, you're all your usual friends, the Jurassic Cretaceous dinosaurs, things like Brachiosaurus and so on. And then earlier it was discussed that the emergence of feathers was something that had morphologically risen during the time of the dinosaurs. Things like Tyrannosaurus rex or the Velociraptors, Archaeopteryx. It's very well known and very well documented that a lot of these animals, or dinosaurs, these reptiles, actually had feathers. So today, oftentimes school children are taught that the difference between different groups of species, like say between birds and reptiles, is that birds have feathers and reptiles don't. Well, in the past, that was not the case in the past, is that these reptiles that clearly fall in the reptile category for the other, they have teeth, they lay eggs, that they're cold-blooded, that fits the reptile, though they were actually feathered, which I think is pretty cool. So that was a morphological change occurring during the Cretaceous, right? Archaeopteryx is 150 million years old back into the Jurassic time period. So this had been occurring morphologically, but it was the mass extinction that, of course, these became the successful creatures, the successful reptiles, there were successful dinosaurs that made it through the mass extinction. And of course, today we know those as birds, right? The non-avian dinosaurs. So what the Cenozoic time period is known as the age of mammals. Again, that's part of that ego thing, but also, we've used mammals for food and for clothing and domestication for a long time. Mammals are really, really important to us in the way that we live. Not only are we mammals, but also they are the creatures of probably the animals of Earth that are most readily thought about. Maybe children, like zebras, lions, things like this. They're charismatic. Mammals tend to be, they're cute and fuzzy and hairy and stuff like this. They suckle their young. They have live birth. So they have little babies, and the babies are all cute all the time. Not like a freaking baby lizard that looks the same as a big lizard when it comes out. It's barely cute at all, right? It's just a little lizard. Okay, they're kind of cute. So anyway, my point here is that this is oftentimes discussed as the age of mammals, but it is just as much the age of birds and an age of insect-flower relationships, where insects and flowers have in some cases co-evolved together to have a certain relationship of pollination. So this flower can only be pollinated by this insect type of thing. And no, those are not details we're going to dive into in any more detail. But what I wanted to point out was that oftentimes, again, after a mass extinction, it is the organisms that make it through the mass extinction that are stronger on the other side. The mass extinction creates opportunities for those organisms that maybe weren't cutting it earlier on. They were just hanging on, right? And maybe like afraid of the dinosaurs and hiding in holes. But after the dinosaurs go away, or other large organisms, there's new niches that are opened up after those. And then lastly, it's oftentimes the lowest organisms in the food chain that make it through, in this case, the Cretaceous Paleogene mass extinction. And I want to point that out again. Organisms lowest in the food chain. Oftentimes, the organisms that are the lowest on the food chain are the most prolific. They're the least specialized. They can be, many of them can have diverse food diets, like omnivores and things like this. So they're a little bit more set up for success. They're not on the teetering top of the house of cards, if you will, or on the top of the pyramid where there's only down to go. So it is the lower, and this doesn't mean that they're any less complex or anything like that. It is the organisms that are lower in the food chain that oftentimes make it through the extinction events to repopulate after the extinction and to exploit new niches. Now we're in the Paleogene, coming after the Mesozoic time period. And I should, before we go much further, draw your attention to, up here I have listed the ppm, or the parts per million of carbon dioxide. And the Paleogene, as an overall average, is about 500 parts per million of carbon dioxide. And let me just quickly back up to the Jurassic for comparison, Jurassic Cretaceous. 1,000 plus more 1,000 plus more parts per million carbon dioxide in the atmosphere. So way up there at 1,700. Now, that'll become clear in here in just a second, but I realized I forgot to point that out during the Jurassic. During the Paleogene, following on the extinction of the dinosaurs, is the diversification of mammals, as we saw in the last slide, that are filling in all of these niches or opportunities left behind from the dinosaurs. And what I think is, this is just from Wikipedia, the Wikipedia entry on mammals, just what I think is really neat is the really large variety of niches that mammals have occupied or do occupy now. So here's from the Wikipedia intro, you have cetaceans like whales. There's the humpback whale, and other seafaring animals or sea-dwelling animals that about 35 million years ago in the Oligocene started as deer, or even, I think, bovine style of creatures, close to ungulates, or maybe forest-dwelling ungulates, I'm not exactly sure, that had been occupying the margins of continents and getting closer and closer to beach or ocean-type environments, and then eventually took the big dip and have become, as marine reptiles no longer dominated the ocean, in the early parts of the Paleogene, that was wide open, and eventually the things like modern-day cetaceans found their way to diversify into such a niche as the ocean. Similarly, the primates, like the modern-day gorilla, orangutan, or the lesser primates like the gibbon or the simang, things like that, which are, and that's us, right? So if you look at this chart in the primate section that's here, you have us that are representing, or Homo sapien that are representing the primates that originally took to the trees, right? Diversified into the niche of being able to climb readily after the Cretaceous. And then another really major group, I mentioned them a second ago, the ungulates, or the hooved creatures that today occupy really large expanses of grasslands and open plains and savannas and things like that. Now, the real point here is just to show that the Paleogene can be thought of as a period of diversification of mammals into all of these amazing niches. And here's a artist rendition of this, a time during the Paleogene where you have leftover remnants of things of the Cenozoic that were very hardy, like the crocs, or I'm not sure if this is a crocodile or an alligator. And then your small ungulates, or small precursors to plains-like creatures that are forest-dwelling browsers. You have maybe smaller carnivores, larger carnivores, and cats. Another style of ungulate, it looks like, and things like the brontotheres, primates that are up here. So this is shown in the artist rendition, and modern-day animals, that all of the things that we know of as cute and fluffy mammals, right, why we think of this as the age of mammals, are all represented by things that have diversified during the Paleogene. So that's kind of why we think of it as the age of mammals, I would imagine. All right, now the Neogene, coming on the tail of the Paleogene, is a much shorter time period and is much, is much more recent, but does not include the Pleistocene, or the modern onset of glaciation 2.5 million years ago, or the following Holocene after the Pleistocene Ice Age, which is the interglacial that we've been in for the last 11,700 years, which is the Holocene, and this also does not include then the Anthropocene, right? Now, so the Neogene here, if we look at that overall biologically, rather than the major changing, and not to say that there wasn't changes in mammals and diversification also during the Neogene, but what sticks out to me, and I feel like to many, soil paleopathologists, or to many people who are studying land vertebrates, a response in the environment of land vertebrates, or a change of land vertebrates, there was a response to the expanding grasslands, or a biologic or botanical change that was occurring during the Neogene. Okay, and again, back to the parts per million up here. Notice this is almost half of the average of the Paleogene at 280 ppm. So notice that the Mesozoic, we were at really high, almost 2,000 parts per million of carbon dioxide, and then we came off of the Mesozoic down into the Paleogene, into 500 parts per million, and now we're well down there at 300 parts per million for the largest part of the Neogene, setting up into the Pleistocene, which has also been at very low parts per million of carbon dioxide. Now, my point there is, last time we actually visited carbon dioxide, just a few slides ago, talking about volcanism, was that we associate carbon dioxide oftentimes with climate change, climatic change. And that's exactly the context here, in that 2,000 ppm, or 1,500 ppm parts per million shift from the warmer times of the Mesozoic to these overall colder times of the late Paleogene, Neogene, and then even into the Pleistocene, which is an ice age. So that trend overall going from warmer to cooler is an overall trend during the Paleogene and Neogene. Now, there have been some climactic optimums in some periods like the Eocene thermal maximum, I believe, that there's been some spikes in there that have occurred that have been overall warmer. So there's a climatic change that's occurring overall during the Cenozoic. But let's back up to carbon dioxide. Recall that the photosynthetic process of plants requires sunlight, water, carbon dioxide. And until this point, until the Neogene, plants having, not just plants, but I imagine all photosynthetic organisms and bacteria, cyanobacteria, the type of photosynthesis that was being used, and I'm not sure if this is the only type, but certainly a lot of grasses, a lot of plants, besides grasses maybe, we're also using this method of C3 photosynthesis, where the carbon dioxide that's needed for the C3 style of photosynthesis is more, is a lot. And upon this decline in carbon dioxide over the last 65 million years, well, I guess that's to now, but over the trend since the Cretaceous Paleogene mass extinction, has been declining carbon dioxide. And now the biology has to respond to that. So overall, these plants are needing more and more access to carbon dioxide to grow and to proliferate, but it's lower. So there was a new invention or a new style of photosynthesis that was developed in the grasses called C4 photosynthesis in plants, and that gave these style of plants a new edge over the others that they didn't need. They weren't as harnessed by the amount of carbon dioxide as the C3 style, or as the C3 grasses. So these plants, they took off like wildfire. They were able to do extremely well in this lower carbon dioxide environment, extremely well in the cooler environment, this cooler trend. Grasslands, if you look overall at the vegetation around the globe today, grasslands do well in more arid environments and more cool environments. And then because of this advantage, they also do well in more CO2-starved environments. So the Neogene became a time period, now looking back paleontologically, became a time period of the expanding grasslands that were filling in the botanical niche left behind by the forests, that it can no longer be sustained with their high amounts of carbon dioxide needed, the high amounts of precipitation. Also we'll see some evidence for an overall drying that's occurring during this time. And overall, the tropical regions of the boreal forests, the tropical forests, boreal forests are in the north, need a warmer climate. So the Neogene can be looked at as a time of expanding grasslands. All right, so to back up, to go over in a different way the last few slides of information, what I've given examples of, starting with even the ammonoids, is to look at examples of how life, morphology of life, how life is shaped and how life is getting its energy, or even how life is reproducing, say eggs, right? Life has been changed morphologically as a response to the environmental changes around it. In this case, the one we just sort of looked over is that grasses, because of the environmental change of carbon dioxide, they changed their kind of biologic or chemical morphology to accept a different amount of carbon dioxide so they could proceed forward. The ammonites changed their shape in their shells, right, their septa, and were able to change with their environment through various mass extinctions until they, of course, met their final end during the Cretaceous Paleogene mass extinction. Things like dinosaurs had also been changing morphology, quite possibly as a response to climate, as the Cretaceous maybe had some cooler poles, and animals there at the poles had feathers for warmth. That's only one of the hypotheses for the rise of feathers in dinosaurs is related to climactic responses. Others are things like mating. But the dinosaurs also had a change after the mass extinction, after opening up the niches for the rest of the environment, birds emerged. And that is definitely a change in morphology from the dinosaurs that existed before that, or the non-avian dinosaurs. Yeah, just put it on the table, hon. So my daughter's back here running around. So that's my hun back there. She found something on the floor. So point is that animals, plants, life in general change as a response to the environmental stimuli that are happening around them. After all, animals can only live in an environment that they can maintain life within. And if you can change something about the way that you live according to stay in your environment, then you can stay. You don't have to move, and you don't go extinct because of the environment. So changing morphology, or being able to change, is an advantage, an evolutionary advantage that organisms have experienced through every single mass extinction, or really in every single type of life catastrophe that we've talked about in this class. That life has remained probably genetically and morphologically flexible enough to take on the new changes. So let's look at another example of life that has changed in response to the environment. In the John Day Fossil Bed National Monument, which is just 100 miles west of where I am here in Ontario, Oregon, is beautiful, beautiful environment there. This is one of the type sections of the what are called the Painted Hills and the Turtle Cove and the Mascal Formation. Actually, this is the daughter that's back there running around. She's a little bit older than that now, huh, Gundi? And so these beautiful formations in the John Day Fossil Bed National Monument, fossil bed is part of that. It's not just that they're beautiful, beautiful sections of rock to look at. They are also extremely fossiliferous. So here's a column of some of the strata that are exposed there in John Day. And then with these dots are a few examples of the flora or the fauna, the plant fossils, flora, or the faunal fossils, the animals that come out of some of these sections of rock. And so those become important. The animals that live in the environment become important for trying to learn about the environment, right? If you find alligator fossils, you would imagine that it's a swamp, right? Or somewhere where alligators could live. It's not a desert. It's probably not a dense conifer forest, something like that. So knowing what type of animals and plants are there certainly limits the type of environment that we know existed during this time. Another thing that really helps us as geologists to understand what the region, the geography of a region was like during one of these time periods is to look at the not just the sedimentary rocks, of course that's extremely important, and not just the animals that were there, but to look at the type of soils that were developing at that time. Soils really do give us a lot of information about the environment that's occurring right now. So today I live in what's called the desert steppes. It's effectively a desertous type of area. If I was to dig a soil pit out in the desert, it has a very characteristic desert type soil profile to it, where it has a thin A horizon, where there's very little organic material mixed with minerals. There's a B horizon, which has been, is that right, or an E horizon maybe, that has been leached of a lot of the minerals, a lot of the soil nutrition, and doesn't have any organics, but it's overall a leached area. And then you might get to something called the B horizon then, that is a zone of accumulation where clays or any of those things that have leached down have accumulated down here. And in deserts, sometimes we get I think it's a BK horizon or a calcic horizon, where these white minerals or calcite, essentially concrete, begin to form down in the soil. So if you've ever dug a post hole out in the desert or out somewhere, in ranch land, you oftentimes hit an area a couple feet down, maybe a foot down, that's really hard. It's a hard layer to get through. Sometimes called hard pan, at least for where I'm from in South Dakota. And anyway, my point there is that's a very typical aridisol. or desert type of soil. So overall, if you look at the soil development that has occurred on different layers or sedimentary layers in geologic rocks, you can determine something about the geography of the soil. If I see record for an aridisol here, I can determine then that that was a desertous style environment. I can cross-reference that with the style of animals that were present in that environment, in addition to looking at the rock itself that that soil developed on top of. I can see that that was, a type of sedimentary rock that may have been there and deposited before that soil developed on it. Okay, so in a nutshell, paleopetrology, or the study of soils, relies heavily on what's called a clorped analysis, where we're looking at climate, I think the overall topography of a landscape, what organisms are present, was it well drained, things like that. So clorped, and then how much time did that take to form is the T that's in there. I don't think I gave all the things, but a clorped analysis is what we're doing here in paleopetrology. Now, if we apply a clorped analysis as Ritalik and Bestlin have done a couple of decades ago, to these soils that are here. So that's why these rocks are so vibrant and so beautiful, is that each of these red layers are representative of a very specific type of soil called an oxisol. Oxygen is in there, and remember, oxygen makes hematite, and hematite's red. So you can kind of relate some of the words that are in there. Is these reddish, these very deeply red oxidized soils with lots of iron and aluminum in them are oxisols, and they are very typical. And you're probably already thinking this, where in the world have I ever seen red soils, right? If you take out a bunch of trees and you scoop up the soil and it's all red, right? Think of any imagery in your mind that you might have where you've seen a scene like that. That's the Amazonian rainforest, right? Or areas of tropical environments near the equatorial latitudes that are undergoing deforestation oftentimes for ranching or farming or cane, a variety of agricultural products. The forest, or at least these tropical style of forests, rainforests, if you will, have been removed. And they expose this red soil that you probably well know is only good for a couple of years because of the deep erosion that occurs to it, because of the low nutrition after all the trees and everything has been removed. But anyway, coming back to the red soil, this desert in the middle of Oregon out here, this desert, eastern Oregon, as part of the rocks that are there, they are literally showing us that 44 or 45, 49 million years ago, these formations were oxisols, 30-some odd million years ago. This is from the Bridge Creek flora. So 30-some odd million years ago, in eastern Oregon, right over here, was a poorly drained, hot or warmer tropical environment with high amounts of precipitation supporting tropical-like vegetation for tens of thousands of years, making what are called oxisols, or tropical soils. So you have that imagery in your mind, that you have a tropical-like environment with big broadleaf trees and swampy low drainage environment. Now fast forward through time, or in geology, we can just walk stratigraphically up to the layers that are sitting above this. Now, because of, this is a slightly different picture. Now, the above this is a slightly younger layer, of course, 29 million years old, and it's conveniently colored green here. This is actually a green rock out here in John Day. It's called the Turtle Cove for that reason. I believe it's called the Big Basin member of the John Day strata. Anyway, not important stuff other than the color, because the color's kind of cool. It was St. Patrick's Day in the real time of recording this about 2 days ago, so green's all in fashion right now. St. Patty's. It's spring. Anyway, back to the paleosols here in the Turtle Cove or Blue Basin member are telling a different story, or they're revealing a different climate than these things. So notice there's no red. The bluish or greenish color is because of the volcanic ashes that were deposited along with these sedimentary strata. So there was clearly volcanism in the region. That was actually the organization of the Cascade volcanoes, I believe, is these started to become a Cascade range, which you can imagine because the Cascades are a rain shadow today on the desert. Before the Cascades, you get warm and you get, well, at least wet weather over here. After the Cascades, you begin to see a rain shadow style effect. Now, the Cascades aren't probably full. They're just organizing. But the soils that are here are mollisols and maybe some weakly developed alpha soils and inceptisols. So an inceptisol is like a baby soil. Alpha soil is a forested soil, but these are weakly developed alpha soils in many cases, which these were also alpha soils or oxasols. Some of these are alpha soils. And then mollisols, which are grassland soils. Aha, that's the key there. So during this time period that are represented by these strata, we begin to see that Neogene rise of grasslands. And look at the timing here, right? This is during the early Neogene or latest Paleogene is what this represents, and we're seeing that in the Paleosols. Isn't that great? This is where the information comes from. All this stuff that we talk about in this class, all these details and stories that I give you, they come from these things, from rocks, from layers of rocks, and reading these pages of time, and we can develop this great understanding of what's happened on Earth. Oh, it still blows my mind. So up from this type of environment, up here in the Gundi Formation, no, it's the Maskell Formation, are these lighter buff-colored rocks here that, again, they do have some volcanic tufaceous input, from what I understand, but they also are mostly mollisols. Excuse me. Mollisols and inceptisols are poorly developed soils that are there. So paleosols, I believe, become less relevant and less important in this time period. And there's overall lesser amount of time of weathering because there's more deposition that's occurring. Overall point there, to go back through this narrative, is that the John Day Paleosols show a trend of drying and cooling through the Neogene. Okay, wet and warm, slightly cooler, slightly drier, dry, and overall cold, or colder. Now, that's related to of course, the parts per million of carbon dioxide in the atmosphere. Lower carbon dioxide amounts, as is noticed through all of these as well, means lower temperatures. Okay, so back to, it's funny, when I first started that slide, I said I was going to tell you about animals, but I was getting there. Okay, I'm getting there. Finally, to tell you a little bit about animals that responded to the cooling and drying trend are modern day horses. Horses that actually evolved here on North America. Now remember, horses are non-native to North America today, that they were brought in by Europeans discovering the new world, and essentially brought in, and then of course the indigenous North Americans or Native Americans were able to use those horses, and then we kind of have the change of Native American culture, which we oftentimes associate as Native American culture. You know, the horse depicted with the buffalo drives and things like this. But horses, modern day horses here in North America, have only been here for a couple hundred years since the European discovery of North America. But what's funny about that is that horses actually evolved here. Okay, so in those same sediments, the John Day age sediments, there are late Eocene horse fossils of things like Mesohippus and Maryhippus. I love that name, Maryhippus. Doesn't it remind you of just like Mary Poppins? And you can just imagine this little tiny horse that's only 3 feet tall, just Maryhippusing, right? Maryhippusing through the forest, right? These small ungulates that began as browsers, eating like blueberry leaves in the understory, something like this, eating sticks and twigs and leafy vegetables. They had shorter, more pointed teeth. They were overall smaller, short, as I said, and had 3 toes or multiple toes, and were a little bit more springy and deer-like from what I have heard. And that slowly developed in the fossil record. The higher in the John Day sediments that we go, the more and more modern appearing these animals get, the horses get, until just at the very top of the John Day section, we don't get to the Pliocene at the very top. Actually, there's a basin over to the east of me in Idaho that is a Pliocene age basin that actually picks up on the geologic story left behind at John Day. And we get to higher strata over here, and there is what's called the Hagerman horse and the Hagerman Fossil Beds National Monument. That is the Pliohippus, or the close to modern day horse. And then they went extinct from North America during the Pleistocene. One of these megafaunal creatures that went extinct from North America. So what I find very fascinating, and this is a story from my own backyard that's right out here, that's written in the rocks, is the changing of the climate that's written in the Paleosols, and the accompanying changing of the animals along with that. So overall, if the forests are gone, horses can't do that for a living anymore, so they start to graze the grasslands. They started as browsers, become grazers, because the climate was shifting from wet and warm to cool and dry. So again, to recap, since the looking at the ammonites and some of these other examples, is mass extinctions, catastrophes, environmental change, all encourage, or they all force animals and plants, or just life in general, to change morphology or habits or niches or whatever it is. If it's going to survive through whatever event, it has to be flexible enough and varying enough and changeable enough to navigate through that. I mean, isn't that just a great analogy for us sometimes as people? When we get to, a rough road or a fork in the road, you got to remain flexible. You got to think about the options in front of you. All of those kind of things. And what's written into our genetic code actually is exactly something like that, right? Is being having an evolutionary advantage. What that kind of, if you unpeel that a little bit, what that means is have a genetic code for variability, for mutations to occur. So a mutation can occur that becomes an evolutionary advantage, and that animal is able to then have a higher advantage in natural selection once it goes through sexual transmission of genetic code. Anyway, I find that all incredibly fascinating, and what the next discussion is that all animals are affected this way, and we as animals are not immune to that, right? This is how we have gotten to this point, right? With thummy thumbs. Okay, well, maybe not exactly the thummy thumbs, but